friends, if I ask you about IO devices, it's very easy to deal with all kind of IO devices, right? IO devices means input output devices. But the fact how your IO devices communicates with each other or with processor is really very interesting. In this lecture, we'll discuss about the concept how your IO devices communicates with each other and also with processor. We'll discuss everything in this video. Also, we'll discuss some of the important synchronization techniques, which is very important for your exam point of view as well. So without wasting your time, let's start this interesting video. So before we move on or before we start the actual discussion, let me ask you a simple question. How many input output devices you can connect to your system or to your computer? The answer is many, and number of input output devices I can install or I can use to my computer at the same time. Now my question is, say I want to play some music, then how my computer will determine that I have to play through that particular speaker only. Forget about a particular speaker. Maybe at the same time I have connected 5 different speakers to my computer. Speaker 1 to speaker 5. All these are IO devices, right? Output devices. And maybe all the speakers I have connected to some different rooms. I have 5 different rooms, and each room I have one speaker. Now I want to play some music to room number 1 only, not room number 2, 3, 4 or 5. How my processor will determine that I have to play in room number 1 only, not to other rooms? So how it will determine? All these things we'll discuss in this lecture. So typically how it happens, how it is possible to decide where to exactly play or where to exactly work with the IO devices, it works based on the addresses. Means whenever you are connecting any IO devices to your computer or processor, there will be some unique addresses assigned to them. You understood that? You have connected mouse to your system, your mouse will get some unique address, say address number 1. You have connected some speaker, address number 2, some projector, address number 3. Now whenever you want to play something, some music through some speaker or through some monitor or through some projector, your processor will know the exact address where to deliver the output or from where to take the input. Understood that? It will deal with the addresses. So it will get the address, it will ask to that particular device, maybe to get the input or to produce the output. This is how it works. So the block diagram will look like something this. There will be some interconnection network. Here you will have processor, memory, IO device 1, 2, 3, 4 and number of IO devices you can connect. Fine. Now as I told you that I will have some unique addresses for each of the IO devices. That means I need some address space where I can store these addresses. Then only my processor will know, right? So there should be some table kind of things where I will store all the information that this address number 1, mouse, address number 2, keyboard, address number 3, printer. So there should be some address space where I will store all this information, and wherever necessary your processor will access that address space, will get the information, and based on that address it will deliver the things, right? Now where to store this information, from where you can use this address space? You have 2 different options. Option number 1, you already have a main memory. So what you can do is you can borrow some space from your main memory, or you can use the same memory space from the main memory to store this information about IO devices or IO device addresses. You can do that. If you are using the same memory space with the main memory or RAM, we call it as memory mapped IO. Fine. Alternatively, what you can do, you can use some other memory space. Instead of using the same memory space with the main memory, you can have a dedicated memory space which will store or which will contain only the information about your IO devices. You can do that. Obviously, it will be a costly one. You have to make one more memory, small memory for that. But that is a possibility. You can do that. If you are using a separate memory space, then we call it as IO mapped IO. You understood that? Now, apart from the addresses, one more important thing you have to know. The important thing is called IO interface. What is IO interface? Say your processor already got the address that I have to deliver this thing to address number 2. I don't know what is in address number 2, but I will deliver there because I know the address. It may be song, it may be anything. Now when you want to, your processor want to deliver this to address number 2, there should be someone to verify it once again. Otherwise it will be very big problem, right? You want to play some music in room number 1, but it's playing in room number 5. So it will be a big problem. Maybe some unexpected thing will be happening. So for that there should be someone in between who will verify it once, cross verify. Okay, processor, you are coming with this data to deliver to this particular IO devices. Let me check it once whether he is the correct one, correct person to receive it or not. So that work will be done by this IO interface. So that means whenever you deliver something to IO devices, maybe you can take input also to output also. It will go through this IO interface first to do a cross verification. And this IO interface is a hardware part. It's not a software. It's a hardware. It's there in your system. And in IO interface, we have 3 major components. Number 1, address decoder. It will check whether the address is exactly same or not, correct address or not. Control circuits. So it will sense what you want to do with the IO devices, whether you want to write something, read something, modify something. So it will check this one from this control circuits. Then we have data and status registers. Sometimes you want to print something. It's not that you press the print button and your printer is working immediately. Sometimes your printer may have some problem. Maybe there is no ink, there is some software issues with your printer, right? So that time someone should tell you that you get some message, right? You get some message box that the ink level is low or printer is in offline mode. Some message you will get, right? So who will sense that? This is status register. It will check whether the IO device where you want to send something is ready to take the data or not, whether it's working perfectly or not. So it will tell you system that. Fine. So this is about IO interface. For each and every IO devices, we have to go through this IO interface only whenever you want to send or receive something from your system. I hope you understood that. So this is how it looks like. For keyboard, display, whatever IO devices is, you will have to go through these 3 things: data, status and control. This IO interface. Fine. Now there is a very important concept. You have to be a little bit careful. If I ask you a simple question, how many words you can type in a minute using your keyboard? Maybe you will say 30 words, 50 words, 60 words, maximum 100 words, 120 words per minute you can type using your keyboard. Fine. If I ask you what is the speed of your processor? The speed of your processor is, your processor can take millions of instructions per second. Fine. MIPS, millions of instructions per second your processor can execute or can take. So you are requesting to send something to your processor. What you want to send? Maybe through keyword you want to type something. Okay. What is the speed of your processor? Millions instructions per second it can take. So your processor is waiting to take 1 million instructions from you in 1 second. But what you are giving? 30 words in 1 minute. Or maybe 100 words in 1 minute you are giving to your processor. When your processor is capable to take 1 million instructions in each second. So there is a huge speed gap, right, between you and your processor. It's not exactly between you, it's between your IO devices and your processor. The speed gap is a huge one. That means you should have some synchronization techniques. Otherwise what will happen? Your processor will be keep waiting to get 1 million of instruction in each second, but you are providing only 100 or 30 words. So it will be a problem. Again, say your processor will send 1 million instruction at a single time to some IO devices, but your IO device can capable of taking only 100 or 30 instructions. So there will be a collision, right? That means there should be some synchronization techniques so that someone will tell your processor, don't send this much information to this device. Your device is ready to take only 30 instructions, so send only 30. Fine. Similarly, it will tell your processor that don't wait for 1 million instruction. Your IO device is capable to send only 30. So you be ready to take 30, not 1 million. Rest capabilities you can work for other devices. Don't keep everything for device number 1. You got it, right? So this is called synchronization techniques. So we have several synchronization techniques. The first important synchronization technique is called program controlled IO. So what is program controlled IO? In program controlled IO, say you have n number of IO devices connected to your system. In this technique, your processor itself will knock each and every IO devices and will ask whether your IO device is ready to take the data or ready to send the data or not. Means, are you ready? Your processor will knock IO device number 1. Hey IO device 1, are you ready? Are you ready to work? If it is yes, then he will send some data or receive some data, whatever. Then it will go for IO device 2. Device number 2, are you ready? Device number 3, are you ready? Device number 4, are you ready? And so on. So like this, what will be happening? Whenever your device is ready, then only your processor will send the signal. Or whenever your device is ready, then only your processor will ask the data. So this, like this, we can do the synchronization. Fine. And this technique is called program controlled IO. Now there is a problem with this one. What is that problem? If I ask you what is your processor is the boss of your computer, right? It's like prime minister of the country. It will decide big things. It will be doing some big decisions. It will taking some big decisions, right? But what we are making our processor to do here? Our processor is working like a chowkidar or peon kind of things, right? When my prime minister should be busy in doing some important meetings with some foreign ministers, visiting foreign countries or doing some important decisions, what I am making my prime minister to do, it's going door to door and asking whether are you ready to take this, whether are you ready to give me this, whether you are ready, right? Unnecessarily, we are wasting the potential of our processor by making do some silly things. Right? So this is a drawback, major drawback of program controlled IO. When my processor is capable to perform some important task, I am keeping my processor busy in doing some small tasks, very silly things. So that is a drawback in program controlled IO. Now, what is the alternate? The alternate is the second algorithm, which is known as interrupts. In interrupts, the thing or the process is completely opposite of program controlled IO. Here, your processor will not go door to door and ask. Rather than that, your IO device will send a signal to your processor whenever it is ready. Fine? Means your boss will be sitting somewhere. Next, your client will send the signal to your boss. Boss, I am ready to take the signal. Boss, I am ready to send you something. So we are doing the opposite thing here now. So it's a better thing we are doing, right? We are not unnecessarily wasting the potential of our boss. Our boss is doing something, and whenever your IO device is ready, it will send a signal. Yes, I am ready to send. Your boss is not going door to door now. Fine. Now this process is simple, and this process looks like very easy. Now the question is why we call it as interrupts. In the previous case, we called program control IO somewhere, okay. But why we call it as interrupts? Because your processor is never free actually. It will be busy in doing some operations. Say your processor is doing some meeting with some other clients. In between, your IO device is sending a signal that boss, I am ready to take the data. So what will be happening? Your boss or your processor will stop the meeting there or hold the meeting there, pause the meeting there. It will come back and it will fulfill the request of the IO devices. So indirectly, what your IO devices are doing, your IO devices are interrupting your processor, right? While performing some regular operations, it is interrupting in between. So that's why you call it as interrupts. So how it actually works like this. Suppose your processor is busy executing some programs like this. And in your program, you have multiple instructions. Instruction number 1, 2. So m number of instructions is there for a particular program which is executing by your processor right now. Suppose your processor has already implemented up to this one, instruction number I, and at the same time some IO device requested for something to your processor, some request signal your processor got. So what your processor will do, it will hold here, or it will stop executing the current program. Rather than that, it will go to the program which is requested by the IO devices. So these are the steps. There may be a number of instructions which was requested by your IO devices. It will be finished all these instructions. Once the request is fulfilled, it will come back to the same stage where it is stopped before. Now, so this program 1, maybe it has 999 instructions and it has completed already 990. So it's not feasible that it will start again from the beginning, right? It's not feasible. So rather than that, what your processor will do is, whenever it's stopping executing or holding somewhere, it will send this address to your program counter, this address. Your program counter will know what is the next instructions to be executed. So whenever this request is fulfilled, your processor will ask the next address from the program counter. Your program counter will return the address where you have to go. So this is how it works. Fine, I hope you understood that. So these are the things I have already discussed about processor. Now we have some important things also to discuss about interrupts. See, suppose your processor is, I told you your processor is like Prime Minister. Your Prime Minister is doing some meeting with, say, President of USA. Fine. Your Prime Minister is busy doing some meeting with President of USA. At the same time, some IO device, maybe some police inspector, or maybe some lawyer or someone called your Prime Minister that, Prime Minister, I need to operate or I need to do some specific task, please do it. Now see the situation. Your Prime Minister is busy doing a meeting with President of USA and someone is interrupting in between. So this is not a feasible case, right? Your Prime Minister cannot say the President of USA to stop there, right? It cannot say that you go and stop there, I am coming, I will fulfill one request which was made by some police officer or someone else, some normal people, right? Because President of USA is very big personality, you cannot make him to wait in between. That means this interrupt should not be entertained every time. There should be some priority. Now how to decide that? There is a concept called enabling and disabling interrupts. Whenever you are performing, your processor is performing a very important task, it will disable the interrupts. Disable the interrupt means no other request will be fulfilled right now because I am busy doing some very important task. So your IO devices needed to be wait. Your IO devices has to wait for some time. Understood that? So how to do that? So whenever you are executing some program, important program, first instruction of the program should be written as interrupt disable. So whenever interrupt disable is written, means your processor will understand that this is the most important task, I cannot entertain any interrupts. So once everything is done, the last line or the last instruction of the program shall be interrupt enable, means everything is done, now you can take the interrupt signal from any IO devices. Fine. So next thing is multiple interrupt signals. So at the same time you can get multiple signals, right? Multiple IO devices may request for some operations or some data. Now how to fulfill these things? How to decide which one is the first one or which one you have to fulfill now? Now for that there are two ways. The first way is, so you will see which one is the first interrupt signal you get. So you may have n number of interrupt signals, you will see which one is the first interrupt signal. Now to get this one, your processor need to visit each and every IO devices and to check, okay, I got some interrupt signal, say X, this is the first signal I got. So now this X signal is sent by which IO devices? Your processor will visit each and every IO devices. Again, it will knock each and every one and it will ask, I got some interrupt signal X. Are you the correct person who sent this one? No. Then go to IO device 2. Did you send this signal X? No. Did you signal this signal X to IO device 3 and so on? So this is one way. Again, if you do this, we are unnecessarily wasting the potential of our processor. The second thing is, your IO device will send some vectored address. Some vectored means some bits of 4 to 8 bits of information. Through that, your processor will directly understand, okay, this is IO device number 1. Fine. Your device itself is telling your processor, I have sent a signal X and I am the correct person. My address is ABC. So whenever your processor is receiving multiple signals, it will check the first one, and once it got the first one, it will check the address which was there with it, and it will directly send or receive the data from that particular IO devices. Fine. Now we have one more concept called interrupt nesting. Means once you are an interrupt, you accepted one interrupt signal. Means suppose I am doing a meeting with our HOD. Meantime, my placement coordinator called me. That means kind of interrupt signal. So I told my HOD sir to stop for some time because I have an important meeting with my placement coordinator. So I went to placement coordinator. Meantime, shall I accept some other interrupt signal or not? Because I am already fulfilling one interrupt signal. Yes, sometimes I have to. When? It depends on the priority. When I am doing a meeting with placement coordinator now, I can take interrupt signals only if I am getting it from some higher authorities like Pro VC, VC, registrar, right? Not from any student. If some student is requesting for something, I cannot fulfill that. I cannot entertain that. But if I am getting something from higher authority, I shall accept whenever, although I am already there in some interrupt request. You understood that? That is called interrupt nesting. So these are the two techniques we discussed. One is called interrupt and one is called program control IO. The third one, these all techniques are nothing but synchronization techniques, right? The third one is called direct memory access. So what is direct memory access? Direct memory access is nothing but a small hardware. I will say it's the replica of your processor. It's a small hardware that can perform many operations like your processor. Not everything, but many things. Many things, some small operations. So that whenever you need to access something, I will not disturb my processor directly to get the data. Rather than that, what I can do is I can disturb my DMA controller, direct memory access controller, which will be the replica of your processor only. Fine. So on behalf of your processor, your DMA is able to reply or respond the data. This is how it works. Fine. And your DMA can be connected with your secondary storage or primary storage as well. So from wherever you need some data or some information, you can ask your DMA. DMA is nothing but a small hardware that acts like your controller. So that's all for this lecture. We'll discuss some more topics in the next video. Thank you.